Hey guys, here's a question. What is the most efficient way to carry in your groceries? There's two methods that people ascribe to. Either you like to take all of the groceries in at once, or you're a more patient person and you can take every individual bag one at a time. It's definitely a certain kind of personality test to that decision. Well, each of these bags has a certain amount of weight to them. And if you want to think of the absolute most efficient way to carry in all these bags, obviously, on paper, the most efficient way of doing that is to carry all of them on your arms at once. However, you need to have a certain amount of ability to exert forces that are strong enough to support the weight of all of those bags. So if each of them weighed 100 newtons and you can only lift 200 newtons, 100 in each arm, then you're only capable of carrying two bags. But if you're stronger and you can do 200 newtons of force in each arm, then you can support the weight of both bags in each arm. You can do all four at once. So imagine an elderly person who maybe can't exert that many forces. It might be more efficient for them to carry in all the bags at once, but that doesn't mean it's possible for them. So efficiency is a good thing, but it's not for everyone. And there are alternate paths to efficiency that can be just as good. It depends on the scenario and the person who's doing the action. Here's another example of this. Another question you could ask is, what is the most efficient way for a pet to enter a car? Obviously, most dogs who are really excited to go for rides will just jump up into a car. But as dogs age, and even for people too, as we age, we become less capable of doing things like leaping high distances. And so one thing you can do for your dog when they get older is get a ramp that allows them to slowly and gradually go up to the height of the car's trunk. So is this efficient? Well, not necessarily. Efficiency means doing something very quickly and rapidly completing the task. So does this match that scenario? Well, no, not necessarily. This actually draws out the process of getting up into the trunk and makes it take place over a longer period of time. So this is not efficient, but it is nonetheless helpful for dogs who perhaps can't muster large forces all at once in their legs. Just like human beings who can't muster large forces in their arms probably shouldn't be doing what's most efficient. So this is going to bring us to our topic for today, which is efficiency. There's a couple different ways we could think about efficiency. In a generic sense, it's defined as the ability to do things well or successfully or without waste. At least this is how we use the word efficiency in the English language most commonly. But in science, and especially in physics, we would define it more technically. We would say that efficiency is a ratio of the useful work performed by a machine or a person compared to the total energy expended by the machine or person doing that action. Now, if that seems a little complicated, that's because it is, but you can think of it in simple ways that will make it easier to digest. And in fact, it's a pretty straightforward concept once you get your head wrapped around it. So I'm going to open up a PhET simulation called Energy Forms and Changes. And this simulation can help us to understand how energy moves in systems. So I'm going to put a little water wheel here, which is going to be powered by a falling stream of water. And I'm going to connect that to a light bulb, which is going to use the energy that's being harnessed by that system. So you can see the water falling, you can see it turning this water wheel, and then you can see that there's a wire connected to the light bulb, and somehow this lights the bulb. But how does water turn into light? Well, it's actually just energy transforming from one form into another. The law of conservation of energy states that energy can't be created or destroyed. It can only be changed or converted or transformed from one form into another. We're seeing that happen here. Mechanical energy is being used to turn the wheel. The water wheel is then probably hooked up to an electromagnet of some sort, which is converting the mechanical energy into electrical energy. You can see from this legend over here that the blue E squares mean electrical energy and gray means mechanical. So then what happens when the energy gets into the light bulb? Well, light bulbs are designed to convert electrical energy into thermal energy because the wire, the filament on the inside of a light bulb, gets very, very hot. And then when it gets hot enough, it can actually emit light instead of thermal energy. So you can see the yellow squares of energy coming off. That's the light energy leaving a light bulb. And it came from originally some other power source, in this case, the water. But you might actually notice that the light bulb has two types of energy being emitted from it. It has the yellow boxes, which represent light energy, and then occasionally it shoots out some red boxes too, and that's thermal energy. Now, do we actually gain really useful work from light bulbs getting very hot? Is that a good thing when light bulbs get wicked hot? Not most of the time. So we would actually consider this heat coming off to be waste energy, whereas the light coming off is useful energy. So all the energy is being used, but not usefully. We're going to keep that in mind as we go forward. Here's another way of thinking about efficiency. When you're getting ready for a test or a quiz, you probably know by now in your education that when you study ahead of time, you do better on the test. So what is the efficiency of studying? Well, let's imagine that you're in an English class and you have two classmates, Bruce and Joanne, and they have different habits of studying. That's probably going to result in them getting different grades on the assessments that they take. Let's say that there's 50 vocab words that Bruce is studying for a vocab test coming up. And he knows all the 50 words that are going to be on the test, so he studies all of them. When he goes in the next day to take the test, he only gets 22 of the 50 words correct. Maybe he was matching them up with their definitions or explaining what each of them means or something, but he only really mastered 22 out of the 50. Do you know what grade he would get? He would get a 44% as his grade. Where does that come from? Well, this is the way that most common assessments are graded. We look at, as teachers, the useful result of what you were able to remember or master or explain really well. And in that case for Bruce, it was 22 vocab words that he knew very well. And then we compare that to the total input, the total amount of information or knowledge that was presented to you or that you were asked to master. And in this case, that was 50. That was the total amount of vocab words. We compare those two by putting them into a ratio, which means there's a numerator and a denominator. It's a fraction, essentially. And then the last very important step we take before we give you your grade is we multiply that ratio by 100%. That's really important because if Bruce's grade did not have that 100% multiplied in, he would have a 0.44 as his grade. And Bruce would probably not be happy about that. He might not like 44%, but it's certainly better than 0.44. So that 100% being multiplied in is very important. Let's now compare Bruce to Joanne. Joanne is also going to be studying the same 50 vocab words. She's in the same class as Bruce, but maybe instead of just staring at her textbook and trying really hard to remember all of the words, maybe she makes flashcards with the definition on one side and the word on the back. And she flips back and forth and tries to use different study tricks to memorize everything. Maybe she studies with friends. As a result, she takes the test the next day. She remembers 46 of the 50 words. What's her grade? She's going to get a 92%. Where does that come from? Again, it's comparing the useful result of what she was able to recall, which was 46. And that's compared to the total input, the information that in entirety was presented to her and that she studied. That was 50. So we make a ratio of 46 over 50. We very importantly multiply by 100% at the end, and the number we get is 92%. So this is efficiency at a glance. And it's not usually the way you hear it talked about. When we talk about technical and mechanical efficiencies, usually you hear it brought up with light bulbs, where there are some types of light bulbs like incandescent that are less efficient, and there are other ones like halogens or CFLs, fluorescent, or LEDs that are more efficient. But what does more efficient really mean? Well, it literally means that it takes less energy to power these more efficient devices, and it requires more energy to power a less efficient device. So you can put the same amount of energy into all of them, and the more efficient ones will be more powerful. In the case of light bulbs, they would glow more brightly or for longer. So that's it at a glance. But the way we'll be seeing it in class is perhaps a little less complicated than everything that exists on the internet. So I want you to focus on just the most basic visualizations of efficiency for now. This is an example of that. This is called a Sankey diagram. This is useful for all variety of things, but we're going to use them to represent electrical efficiency of devices. So you can see in this Sankey diagram that there's 100 joules of electrical energy being put into an incandescent light bulb. And Sankey diagrams show total input energy, which is that 100 joules. That they also show the useful energy being used by that device. And in this case, there's 10 joules of light energy that is being emitted by that light bulb. The last thing a Sankey diagram shows is the waste energy, the energy that does not get used for the useful purpose of the device. And in this case, that's 90 joules of heat energy. Now, in these Sankey diagrams, the horizontal arrows represent useful energy, and the arrows that dive down represent the wasted energies that can't be used anymore. So in an incandescent bulb, 100 joules of energy is presented to the device, is pumped in, and 90% of that energy is lost. Compare that down below to an LED bulb, you might get something that looks more like this. Out of the 100 joules of total input energy, 75 joules of light energy is emitted, and 25 joules of heat energy is emitted, and that's the waste energy. So you'll notice this bar here is really thick. We got to use and keep a lot of this energy that was originally put into the device. So this is a more efficient machine. Now, could you figure out exactly how efficient these two are? Yes, you could. This would be 10% efficient, and this would be 75% efficient, which is obviously much better. Now, how do you calculate that? Well, you're going to need something called the efficiency equation. This is what we'll use in all scenarios to figure out how efficient a machine or a person is. So let's take a look at what that equation is. Here's the efficiency equation. It says efficiency equals the useful work done by a machine. Now, you'll hopefully recall that work is actions that we accomplish using energy. So that useful work done could mean pushing a box or lifting something up. That gets divided by total energy input. That's the energy or fuel that goes into that action. And then finally at the end, multiplied by 100%, that simply turns it into a real percentage. So let's look at what kind of situations this could be useful for. Imagine a human being going for a run. How much energy do we actually use in our bodies to make us move forward? Well, it turns out human beings are not very efficient. In fact, we use very little of the energy contained within our bodies to move our bodies around. And that's because we have a lot of things going on in our bodies. Our neurons are firing, our heart is beating, our stomachs are churning and digesting food, and movement is just one of a million things that we're doing at any one given time. So here's just a very rough example. If a person is going for a run and they need to do 300 joules of work in order to transport their body from one place to another, it's very likely that the numbers will look something like this. They might have to put in 1,200 joules of energy just to get themselves to that point where 300 joules of work was actually done. And that's because their body is highly inefficient. In fact, on average, when it comes to moving our bodies around, the human body is around 25% efficient, meaning you lose 75% of the energy that goes into motion through other things in the body happening. It could be heat leaving the body. It could be sounds that are emitted. There's all sorts of ways we can lose or waste energy when it comes to motion. And again, it's because human beings do so many things other than just move around. We're multifunctional devices. When you compare human beings to something like a car, energy efficiency changes pretty significantly. Again, these are rough numbers, and I'm making up numbers that are reasonable rather than completely accurate. A lot of cars are different from other cars in terms of efficiency, as you probably know. So let's say a car needs to do 300 joules of work, just like the human did. Instead of 1,200 joules, you might only need 600 joules. It's still not perfect. You're still wasting 300 joules of energy and only keeping half of it, but that's more efficient than before. In fact, that's around 50% efficient. Now, we could wonder, where does the waste energy go for a car? What kind of waste energies come off of it? Well, the same thing as a human. Heat is constantly emanating off of a car. If you turn your car off and you put your hand immediately on the hood, you're going to feel a lot of heat coming off. And if you're on a quiet street and you close your eyes and a car goes by, you know how you can tell? You can hear it. It goes, so there's a lot of sound energy coming out. So sound and heat, those are waste energies. What's the good kind of energy that we want a car to use? That would be kinetic energy, the energy of motion. So that's the 50% we get to keep. And also a little bit of electrical energy too to power our radios and other devices inside the car. So why are cars more efficient than human beings? Well, remember, human beings are inefficient because we have millions of things going on inside our body at any given time. So we're not really optimized for any one particular task. Well, cars can be more optimized because they have less things they need to do. They have to drive forward. They might have to drive backward once in a while. The radio needs to turn on. Lights need to flash. There's maybe like 50 things at max that a car needs to be able to do really well, and everything else doesn't really matter. So it can be optimized for that job a little bit better. When you get from a car to something like a refrigerator, though, you can reach what is perhaps the maximum levels of efficiency that devices can possibly have, because that refrigerator is just sitting still, doing one job, keeping things cold, and that's it. Now, realistically speaking, it might have a freezer in it that's colder, and so technically that's two different tasks, and maybe there's some lights, and maybe it makes ice or something like that. So let's say that if a human has a million things going on in their body, and a car has 50 things going on, a refrigerator might have like 5 things that it needs to be really good at. So it can be more efficient at those jobs. So if a refrigerator needs to do 300 joules of work, it might only need 400 joules of energy pumped in, and it loses 100, but it keeps 300. So that's a lot more efficient. And in fact, in this mathematical scenario, that would be 75% efficient. So if I'm saying that this is the top of the mountain and there's nothing more efficient than a refrigerator or any device that just sits still and does one thing, that begs the question, can there be 100% efficient devices? And the answer is, unfortunately, no. It is physically impossible to design a contraption that is 100% capable of keeping all the energy that you put into it and doing just one thing with that energy. It's inevitable in our universe due to friction and air resistance and other things that energy will spread out. So last little note here about the efficiency equation. There are some key words that you'll eventually see in your physics problems that might be helpful to you when you're trying to figure out, is the energy that's being described to me right now the useful work being done, or is it the total energy that got put in? Like, for example, down here with the car, you might be told the 300 joules and the 600 joules, and you might not be sure which one is which. Like, where do I plug that in the equation? And here's how you can figure that out. The keywords that can be useful in describing this numerator here, the useful work done, that's an amount of joules you'll need to plug into a formula. And the keywords that you'll see used alongside this variable here is words like ideal or hypothetical or minimum. When you see these words, it's likely that the question is referring to the useful work done by a device. Likewise, for total energy input, there are some keywords that usually will tell you that you're looking at this particular variable, not the one in the numerator. And that is words like real or actual or total. Another trend you can think about is that the total energy that you put into doing something will always be larger than the useful amount of energy that you get to keep. So when you're given two different energies in a problem and you're not really sure which one goes where, remember that the bigger one should go on the bottom and the littler one should go on top. Okay, so now we're ready for our practice problem using efficiency. Here's our problem. A girl who weighs 600 newtons decides to take the stairs to her second floor apartment instead of using the elevator. This is going to be a three-part question, so here's the first part. How much work does the girl ideally need to do in order to climb up the 5 meters? Okay, so they ask for work in this problem, so I know I need to use the work equation. Work equals force times displacement. But what's the force? Well, I know that this girl weighs 600 newtons. That's the downward pull from gravity that is acting on her body at all times. And so if she weighs 600 newtons, and that's the pull down, that's the force that she needs to fight against in order to lift herself upward. So that means her upward force to get up the stairs is also going to be 600 newtons. The last thing I'm going to need to think about is her displacement. How far is she going to get? Well, in terms of how far she gets away from the Earth, fighting against gravity, that's going to be 5 meters. Now, this journey up the stairs here might not be 5 meters, but the vertical distance she's traveling, which is the only distance that matters here for gravity's sake, that's 5 meters. This might be like 12 meters or something, but the only thing we really care about right now is the vertical displacement. So here's what we would do. Work equals force times displacement. The force is equal to 600 newtons. The displacement is 5 meters. 600 times 5 is 3,000. So this girl, ideally, at minimum, will need to be able to muster up 3,000 joules of energy just to barely get herself up to the top of that set of stairs. Now, you guys know from what we talked about earlier that the human body is not very efficient. In fact, it's around 25% efficient. So if she only puts 3,000 joules into getting herself up the stairs, how much is she going to get to actually use? And how much is just going to be waste energy that leaves her body as heat and sound? Well, it's going to be 25% of 3,000 that she gets to actually use. So that's not going to work. She can't put in 3,000 joules and expect to get up the stairs. That would only work if she was 100% efficient. So this problem isn't really done. We need to throw in some efficiency stuff in here. Here's the second part of this problem. The girl's legs actually exert 12,143 joules of energy while climbing the stairs to the second floor. What is the energy efficiency of her legs? Okay, so in this problem, we're being asked for efficiency. We learned a formula today that says efficiency equals blah, 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 blah. So let's put that equation in. And here's that formula. Efficiency, which is usually symbolized by an E and a percent sign. Efficiency equals useful work out divided by total energy in, and then times 100% to turn our answer into a percentage. So we have to identify where these numbers are going to come from. Useful work out, total energy in, what are these things? Well, both of them are going to be measured in joules because energy is measured in joules and work is also measured in joules because we need energy to do work. So they have the same unit. So the fact that this says joules and our answer in the last question is joules, that doesn't really tell us which one is which. But we know that those are going to be the two numbers we use because they're both measured in joules. So the girl's legs actually exerts 12,000, and ideally she would only need to do 3,000. I'm getting the sense that this larger number is the one that should go on the bottom, and that this 3,000 is the number that should go on top, because the thing that she's going to accomplish at the end of the day is getting her body up higher than it was before, and her body will have this much more energy in it. She'll have done this much work. But a lot of the energy that she used to do that work will have been wasted and went away. So the real energy she puts in is going to have to be a higher number than this 3,000. So that must be the 12,000. So I'm going to remember that the bottom number is always the bigger one, and I'm just going to put that bigger one in the denominator. So now our math is going to look like 3,000 joules of useful work that she does by climbing the stairs, divided by the total energy she had to put in, which is always the larger one at the bottom. That was 12,143, and then times 100% to make it a percentage, and our answer comes out to 24.71%. So that's the efficiency of her legs. Does this seem reasonable? I would say so. First of all, because you heard earlier in this lecture that humans are around 25% efficient, and I really mean around because it fluctuates dramatically depending on what we're doing and who the person is. So that's the efficiency of her body. We should also check to make sure that it's reasonable, that it's not over 100% or even 100% at all, and it shouldn't be below 0. So anywhere between 0 and 100 would be a reasonable answer. So where does this leave us for our final part of the question here? Well, now instead of taking the stairs, she's going to take the elevator, and we'll see which path is more efficient. The next day, the girl takes the elevator. The elevator uses a total of 6,579 joules of energy in lifting her up to the second floor. What is the elevator's efficiency? So can we make a prediction here? Is the elevator going to be more or less efficient than taking the stairs? Think about how the human body is designed for all sorts of things, and an elevator is designed for pretty much one thing, maybe two, depending on how you look at it. So the question asks, what is the elevator's efficiency? So we're going to use the efficiency equation as we did in the previous part of the problem. So efficiency equals useful work out divided by total energy in times 100%. So what numbers go where? Well, this 6,000 number is the energy that the elevator uses, and the 3,000 is still the amount of energy that she will have done by moving upwards. She's still going to go up 5 meters. Even though she's taking the elevator instead of the stairs, that doesn't change where she ends up. She still ends up 5 meters up. And her weight doesn't change. She still weighs 600 newtons. So these two things are still true. So whether you go up the stairs or go up the elevator, the work that's done by moving this girl upwards is still 3,000 joules. So what's different about this problem than the previous one? Well, in the previous one, her legs did the work, and they did 12,000 joules of work. And in this time, the elevator's doing the work instead of her legs, and it does 6,500 joules. So that's the amount of energy that's used. That's the bigger number. Comparing the 6,500 to the 3,000, this is the bigger one, so it should go on the bottom. So our math looks like this. 3,000 divided by 6,579 times 100 gives us an answer of 45.6% efficient. So does it make sense that the elevator is more efficient than the human legs? I would say so, because elevators are designed to go straight up and go straight down, and sometimes light up a few buttons. And that's pretty much all they do. So elevators are highly optimized for that task. Now, again, these are made up numbers, but they are reasonable numbers, and it really depends on how a machine is constructed and the engineering that goes into it, how efficient it is. So it's really important that you study physics and understand how these things work, because one day you may be asked to build or construct or fix something, and you need to keep in mind how energy efficient those things are going to be. Okay, I hope that was helpful, and I'll see you in the next video.